Hello to all participants and observers of the RPPM Hackathon. Today's lecture will be delivered by Professor Kilho Shin from Gakushin University in Japan, who will introduce Fourier decomposition and Koopman mode decomposition, two powerful methods for time series analysis. Fourier decomposition breaks down functions into fundamental components, while KMD extends this concept to dynamic systems, capturing their evolution over time. These approaches are widely used in modeling complex phenomena, including air pollution analysis. Enjoy the lecture.
Time series analysis can be a key approach when modeling air pollution data. In this lecture, we introduce two powerful tools for time series analysis: Fourier decomposition or FD and Koopman mode decomposition or KMD. Both aim to represent a function of time using a countable set of features in theory and in practice a finite number of features. By analyzing these features, we can identify major causes of observed phenomena or uncover relationships between them. As a method, KMD extends FD, and both share a remarkably similar theoretical foundation. First, let's introduce a function space defined over a finite space. Consider the set of integers from 1 to n. Any complex valued function on this set can be represented as a vector of n complex numbers forming an n-dimensional complex linear space. Moreover, we can naturally define an inner product in this function space. Next, we extend the function space from a finite set to the case where the domain consists of all natural numbers. Also, each function is now a sequence of infinitely many complex numbers. We can still interpret it as an infinite dimensional vector. So when introducing the inner product, we need to restrict the class of functions. This is because the extended definition of the inner product involves an infinite sum of component-wise products, and we must ensure the convergence of this sum. To ensure convergence, we impose a condition on the functions included in the function space. Specifically, a function must satisfy the condition that the sum of the squares of the absolute values of its components converges. Using the Wheatland-Schwarz inequality, so we can prove the convergence of the inner product mentioned in the previous slide. We can further extend the domain of functions from a discrete set to a continuous one. Here, we assume the domain is an interval from 0 to 1. Just as when the domain consists of natural numbers, each function can be viewed as an infinite dimensional vector, although its components now form a continuum. Under the assumption of convergence, the sum used to define the inner product can be replaced with an integral. Recall that an integral is simply a continuous sum. The convergence of the inner product follows from restricting functions to those that are square integrable. This means that the integral of the square of the function's absolute value must converge. Just as we saw earlier, the convergence of the inner product also follows from the Schwarz inequality. Now we have the L2 space over the interval from 0 to 1, which is an infinite dimensional linear space equipped with an inner product. The key fact for Fourier decomposition is that this space has a basis consisting of the functions expressed as e to the power of 2 pi I n x, where the symbol I represents the imaginary unit. Therefore, any function in L2 can be expressed as a linear combination of these basis functions. As we will see in the next slide, the true nature of these functions is that they correspond to trigonometric functions. The fact that the basis functions for FD are trigonometric functions follows from Euler's formula, often regarded as the most beautiful mathematical formula ever discovered. Additionally, the polar representation of complex numbers plays a crucial role in understanding KMD. Koopman mode decomposition, like Fourier decomposition, provides a way to decompose a function, but it uses a different basis. In both FD and KMD, each basis function is typically a complex constant raised to the power of x. However, in FD, these complex constants are restricted to having an absolute value of 1, whereas in KMD, they can take any value. As a result, the basis functions in FD are always periodic, while those in KMD can exhibit amplification or decay. Because of this difference, FD is limited to decomposing periodic functions, whereas KMD can decompose functions that exhibit amplification or decay. More specifically, KMD represents a function as a sum of exponentially amplifying and decaying waveforms. It is worth noting that FD can be seen as a special case of KMD. When observing a function in practice, so we can only access a finite set of its values. Therefore, when performing FD or KMD in real-world applications, so our goal is to compute a decomposition that best fits or approximates the given values. There is a difference in how function values are treated in FD and KMD. In FD, the values are scalars, whereas in KMD, they are vectors of common dimension. However, the difference is primarily historical and not fundamental. So for a practical implementation of FD, we introduce a method known as the discrete Fourier transform. As for KMD, various methods have been developed, but we will focus on one of the most well-known approaches called dynamic mode decomposition. The discrete Fourier transform computes t coefficients of the transforms from t observables by solving a simple system of linear equations. Due to the properties of trigonometric functions, we can see that considering only t components is sufficient for FD. In discrete Koopman mode decomposition, the set of unknown variables expands to include both the number n of decomposition components and the eigenvalues mu1 to mu_n. As a result, the system of equations we need to solve is no longer linear, making it significantly more challenging to solve. Various methods have been proposed in the literature to address such systems, including dynamic mode decomposition. Since its introduction in 2008, dynamic mode decomposition, or DMD, has been extensively studied, leading to numerous variations. The fundamental principle of DMD is to find a square matrix A that maps observables from time 0 to t-2 to those from time 1 to t-1. Such a matrix does not always exist, but when it does, it can be computed using the Moore-Penrose pseudo-inverse. The eigenvalues of this matrix, denoted as mu1 to mu_n, are precisely the eigenvalues of KMD. Fourier decomposition, or FD, and Koopman mode decomposition, or KMD, are both powerful tools for time series analysis. FD decomposes the periodic function into a sum of trigonometric functions, while KMD extends the concept of functions that exhibit amplification and decay. Both provide a linear decomposition of a function with respect to their respective bases within a function space. To ensure accurate results, make sure that the sampling rate is appropriate and that the time series is sufficiently long. Since noise can impact analysis, applying prior noise reduction is recommended. Additionally, using a window function can help mitigate spectral leakage. FD is most effective for stationary time series, while KMD tends to be more sensitive to noise. KMD can also be computationally expensive, especially for large datasets. To improve efficiency, consider using methods such as sparse approximation and dimensionality reduction.
Thanks for watching. We hope this presentation has sparked some ideas and gave you useful insights for your projects. If you haven't already, head over to www.rppm.org and learn more about the hackathon and sign up. Because, let's be honest, the best ideas happen when you're in the game, not just watching from the sidelines. Good luck, have fun, and see you in Japan at RPPM.